Hi, it's John Williams here at MIT. So let's take a look at hashes and exactly how they function. So here's a simple example of a hash that we take the text in a document. So here we've got hello, and we assign values, say, to those characters. So here H is 8, E is 5, L is 12, etc. And in this case, the hash function is just we sum these values. So we get a hash of 52. Now, the hash is like a fingerprint in the sense that if anything in the document changes, let's suppose the E here changed to an O. So now instead of E being 5, it would be an O, it would be 15. So there'd be now a total of 62. So the hash would change quite radically. So let's take a look now at a different kind of hash function. This one is that we just take the modulus of the number. So for example, here 25, we divide by 15, goes once, and the remainder is 10. So the hash is the modulus, it's the remainder that we get when we divide by 15. So in this case, we could store these numbers, for example, in an array that's 15 long, 0 to 14, because we'll always get a remainder of either 0, 1, 2, 3, up to 14. So no matter what the number k, it'll be put into one of these bins. In some sense, we can view the hash as a key that will tell us exactly where the value is stored. So if I know the key is, for example, 5, then in this case, I know that 35 is stored there. This is another example of using hashes to bin things, and that's the way it's used in Bitcoin and blockchain. So here's another property of a hash so this is a real hash function, a SHA-1, and if the input changes just by 1 bit, you see that we get a radically different output. So flipping 1 bit of input, over half the bits of the output are changed. We can use Merkle trees to lock down documents. In this case, we're taking a series of documents, we're calculating their hashes, and then we combine pairs of hashes and hash those to get a single hash, and eventually we get a Merkle, what's called a Merkle root, the top hash here, the root of the Merkle tree. Now, if any document changes, this top hash changes, and that's the way it's used in blockchain, and we'll come back and examine that in more detail later. Okay, so now let's take a look at a real hash function. So here we've chosen SHA-1. We've got a choice of various hashes. Now let's put in, for example, H, E, L, L, O, and you see that we've got a radically different hash every time. This is a typical. Notice there, this hashes and it starts with a leading 0. In blockchain, when we need to solve a puzzle, we need to alter a document so that we get a number of leading zeros. So here we've got 1 leading 0, and that occurs quite often, but to have, say, 6 leading zeros, well, we'd have to experiment quite a lot. You see here, document, there was another 0. But we haven't got 2 zeros. So I'll maybe give you this to play with, see if you can get something starting with leading zeros. Usually what people do is they take the document and then they add something called a nonce, a number to it. So I'd add 1, 2, and you'll see by luck we might get something with leading zeros. So far we haven't, but you get the idea. Okay, so maybe you'll play with that.